This is going to be a quick video on PCA, assuming you have a brief linear algebra background. So PCA is just kind of a way to simplify your data set so you can visualize it easier. Maybe you have a bunch of variables and it's hard to kind of plot your data and everything. So here's an example with n people and m variables that we measured for each person. So let's say we have 30 people and we ask them each their height, weight, and IQ. So we can organize this data. We could have xi be the column vector representing all the measurements on the ith person. So there's 30 of these guys. So the first one could be like 1.8 meters, 70.3 kilograms, 105 for IQ. So we see that each person is a point in R3. In general, it'll be Rm for the number of variables you have. So with these three variables, we could plot this in 3 dimensions, maybe kind of see how they correlate with each other, all the variables. But for m greater than 3, you can't really plot that. Maybe you could do like color for a fourth variable or size, but even that gets kind of tricky. So yeah, is there a way to look at the data while still seeing the relationships between the variables? So maybe even though we plot our stuff in R3, all the points might be localized on some sort of plane, or in R4, maybe they're all in some hyperplane of some sort too. Let me fix this here. And then from that, we could kind of see which variables are correlated. If they're so in R3, if they're on a plane, maybe we can see that there is a pretty strict relationship between two variables. So height and weight, for instance, might be correlated. People who weigh more are taller. But, you know, IQ might not go in the same direction as that. Same with height. So here we say, even if we have two variables, could we move it to a line maybe, so we could see that all the variability is based off that one line? So let's do a little math background here before we move into another example of PCA and how it works. If A is an m by n matrix here, m rows, n columns, so here we have our example, 3 by 30 matrix. If we make it symmetric, then the eigenvalues are necessarily real. And that helps for PCA because the eigenvalues or eigenvectors are the directions of the variability. So we need real eigenvalues so we can actually have a physical representation of them. So in our example, 3 by 30, it's not symmetric obviously, but there's a fact that A transpose or A transpose A are symmetric. So here we have some properties of that. They share the same non-zero eigenvalues, whether we have the 30 by 30 matrix or the 3 by 3 matrix. And if we have the eigenvector of A transpose A, then if we left multiply that by A, then that's the eigenvector of A transpose. Similarly, we have here, if W is the eigenvector of A transpose, left multiplied by A transpose, we have the eigenvector of A transpose A. So if A is the 3 by 30 matrix, to find the eigenvalues of the 30 by 30 matrix, all you have to do is find the eigenvalues of the easy 3 by 3 one, and we can tell that the other 27 eigenvalues are 0. And so all the eigenvalues are non-negative also. Background and statistics here. Sample mean of variable A, pretty easy, just the average everyone's used to. Sum up all the samples, divide by the number of samples. And then a measure of the spread is the variance. You've probably seen this before too. Sample variance is just defined as the difference between the mean and the sample. You square every sample, sum them up, divide by n minus 1. So the covariance of two variables, also not too bad. A and B could represent two different variables, say height and weight. take the mean of the height, subtract it from the person one's height, do the same thing with person one's weight, subtract the average weight from it, and you just sum all those up and then divide by the number of samples. So we can see that if A here is the same as A is B, then this is just the definition of the variance, because this would be the same exact value as this here. So here's just a simple notation for the covariance here. Sum over all the people of the two different variables. And then we can have a cool little covariance matrix here. Let's say we have 3 variables here, and we organize it in this way. We can see that if we take the covariance of height and height right here, then these two are the same, which it just gives us the variance. Here, if we do the covariance of weight and height, it would be, let's say, weight here, height here. That would be the same thing as taking height, weight here. This quantity will be the same. So we see that this matrix is going to be symmetric, and the diagonals are the variance of each variable. Just a little note here, negative covariance means that as one variable increases, the other decreases. Okay, now for PCA. So we could store the mean in a single vector, mu, and mu is an m by 1 matrix. And basically it's just the average of each variable. So here's sum of all the heights of each person divided by the number of people, sum of all the weights of each person divided by the number of people, same for the IQ. And we can write this in this little compact format here. Now we want to recenter the original matrix. Let's say this is height, weight, IQ for all of our n people. For PCA, we want to recenter all these values around the mean. So if this is our original matrix A, B would be that recentered matrix. So we can see, okay, 1.8 minus the average height, that's 0. Let's see, 1.6 minus the average height would be minus 0.2 for person 2, so on here. Let's say IQ is 100 for this person, average IQ is 105. Subtract the mean, we'll get minus 5. So you see how that works. And then just a neat way to put that here is, this is all of person 1's variables subtract the mean of all those variables. So each of these entries is a column vector in itself. So we have n of these column vectors. Now, covariance matrix, as we just saw, we can express that as 1 over the number of samples minus 1 times B transpose. So if we go back here, we want that to be in the form of this summation right here, where A is one variable, B is the other variable for each person. So this covariance matrix S here is going to be m by m, where m is the number of variables. So that means we're going to have a matrix that displays how each variable varies according to other variables in our little example. So here's B transpose. Let's say we want the second row, first column. So matrix multiplication here. That'll be A2 minus mu2 times A1 minus mu1 right there. And then B2 minus mu2, B1 minus mu1, and then C1 minus mu1, C2 minus mu2. So if we put that over here, this will just be the covariance of those two variables, A and B. So now let's do an example with two variables here. Each point is a person then, and we have their IQ and weight. So we see that the weight captures most of the variability here. There's some vertical variability with the IQ, but it's not very correlated with the weight. And let's say we have our covariance matrix here. We see that weight, there's a large spread, 95, and the IQ spread is, 1/20th of that almost. Not a lot of spread there. And we see there's not a lot of correlation between IQ and weight, so the covariance of those two variables is going to be very small. Whereas over here, we have weight and height plotted together. Now those intuitively are going to be correlated. That's reflected in the covariance matrix here. The spread of each is equal, and we can see that there's a positive correlation between them. If this was negative, then we'd have negative signs for the covariances. So the eigenvectors of this covariance matrix will tell you the direction in which the variability is highest. So let's see here, the first eigenvector with the greatest eigenvalue is in the direction of the weight axis. The second eigenvector is going to be the vector orthogonal to the first that has the most variability also. So here with 2 dimensions, it's the only one left, which happens to be in the IQ direction. But if this was multiple dimensions, then the second eigenvector could be in some direction of variability, and here we can just ignore this one because all we care about, we can see, is the weight and captures most of the variability. Here we can see that the eigenvectors are pointed again in the direction of variability. So here's the most variability, and then the second most that's also orthogonal to the first. So both of these distributions are a thin strip, but the covariance matrices are very different. And our end goal here is to dimension reduce everything here. So we kind of want this strip to model this one a little bit. And the way we do that is we rotate this distribution about its eigenvector. So we want a normalized eigenvector, so its magnitude is 1, and we want just the rotational aspect of that. We don't want to scale the data at all. So yeah, we want to reorganize the data so that most of the variability occurs along the axes, just like in the left figure. So in the left figure, we have 2 dimensions being reduced to 1 dimension of variability here. In 3 dimensions, maybe there are 2 axes of variability that we care about, or maybe most of the variability occurs along a certain line in 3 dimensions. Same thing with higher dimensions, etc. So it also doesn't always help to use PCA. For instance, if we have large spread in each direction, dimension reducing this, we lose a lot of our information about our distribution. It wouldn't really help us categorize any of our data. So we want to rotate something that looks like this into something that looks like this. Now the new axes, these are the principal components. So here's principal component 1, which is direction of the most variability, which is along U1, the first eigenvector. And then PC2 is direction that's orthogonal to PC1 that has the second most variability, which happens to be the only dimension we have left. So in the 2-dimensional case, when we simplify it, there really only goes down to 1 dimension, which we can see here. So recalling our linear algebra knowledge here, S is symmetric, you know it has real eigenvalues. So in 2 dimensions, eigenvalue 1 greater than eigenvalue 2, then eigenvector 1 is direction of most variability, as we see here. So good PCA keeps the majority of the total variance displayed on the axes because we don't want to lose any information. So the total variance of our distribution we'll call T, and that's just defined as the trace of S, or the sum of its diagonal values. So here we can see the total variance of this would be 100, or the sum of these two diagonals. And if we calculate the eigenvalues and eigenvectors of that covariance matrix here, 50, 40, 40, 50, we see that the first eigenvalue is 90, the second eigenvalue is 10. The first normalized eigenvector, so its magnitude is 1, is up in 45 degrees, and the second one is that way, 45 degrees. So we can see the ratio of variance that we're keeping by doing this principal component analysis. And if we only use one axis, we're keeping lambda 1 over the total variance, which is, in this case, 90 over 100, 90%. So 90% of the variance of this is kept in just one axis. Now if we do another example in 3 dimensions here, let's take 100 bird species, measure 3 variables about them: length, wingspan, weight. Here's our centered matrix of all the lengths, wingspans, weights, centered about the means of all these 3 variables. Here's our covariance matrix here. We can see it's symmetric, so we don't really need to fill in these other values. And if we just go ahead and calculate the eigenvalues and eigenvectors for this, we can see that eigenvalue 1 is huge, which means if we divide the total, if we divide this by the total variance, we see that it still keeps 92% of the total variation in the data in just that one principal component axis that we're going to have along this corresponding eigenvector. And if we look at the second eigenvalue here, we see that 7% of the variability is maintained in that principal component axis. And then this would be a rough plot of that eigenvector corresponding to that principal component. So an interpretation of this, after we kind of transform all of our data into this kind of 2-dimensional plane, we're keeping whatever, 92 plus 7, we're basically 99.5% of the total variability in this data is represented in this 2-dimensional graph. So we can totally get rid of one dimension, which makes visualizing this much easier. And furthermore, we can see that most of the variability is maintained in this one principal component. Interpretation for that principal component is when we study these 100 bird species, analyze their length, weight, wingspan, really only 2 factors corresponding to the 2 principal components are important in characterizing the relationships of these species. So the first axis, the one with the largest variability, we can pretty much interpret that as the size. We see that the weight here, since it's the greatest magnitude in that first eigenvector, the weight is the most indicative of size, and a change in 1 unit of weight affects size more than the length or the wingspan. So here, 8 up for weight, 4 across for wingspan, 2 down for length here. Kind of see that this principal component aligns itself with weight a lot more than the others. The second factor in these species we could call stoutness, maybe. We see that as the wingspan goes up, the weight goes down, and those are the 2 most prevalent variables in this eigenvector here. You see that wingspan is the most important in this eigenvector, and the second most is the weight. But we see kind of a negative relationship here. So as wingspan goes up, weight goes down, and here's that second eigenvector plotted out here. And stoutness, maybe you could visualize as here's like a stork-looking bird, really wide wingspan, lighter weight than this fat turkey with a short wingspan. Yeah, so that's principal component analysis, taking in a lot of data with a lot of variables, finding the correlation between all the variables, and plotting it so that we can see what's really important in that data, what factors capture all the variability.